We have been discussing on the eigenvalues and eigenvectors of a square matrix, and which I said will be important if we try to understand the fundamentals behind the direct iterative method solvers, the convergence of an iterative method solver, especially for the direct iterative solvers, or the conditions under which the direct iterative solvers will work, or some modifications will work on these solvers. The eigenvalues and eigenvectors will be important, and we started with the discussion that eigenvalues actually arise from the solution of ordinary differential equations or rate equations expressed as combination of several variables. So, we have gone through an example to see how eigenvalues and eigenvectors can be computed and made few observations on them. And in the present class, we will look into more on the properties of eigenvalues and eigenvectors. So, we discussed about distinct eigenvalues and repeated eigenvalues as the roots of the polynomial, characteristic polynomial. So, for repeated roots, the part where we ended, for repeated roots, the associated eigenvectors are null space vectors of the same matrix A minus lambda I. So, there is one lambda which is arising thrice or more than once, thrice is an example, arising more than once as the solution of the polynomial equation. So, this when we will write A minus lambda I, this particular lambda will introduce more than one 0 pivots in the echelon form of the matrix. So, there are more than one dependent columns in the matrix, therefore, there will be multiple eigenvectors, because the number of dependent columns will give us what is the dimension of the null space. So, geometric multiplicity, and this is for real symmetric matrix, we can see exactly the number of times the eigenvalue is repeated is the number of eigenvectors associated with it, which is called geometric multiplicity for real symmetric matrix. And null space vectors are linearly independent. So, for one particular eigenvector, when it value when it is repeating, all the eigenvectors associated with it, at least for real symmetric matrix, they are linearly independent. Now, what we will try to explore is that eigenvectors for distinct eigenvalues, when it is not repeating, when there are distinct eigenvalues, lambda 1, lambda 2, lambda t, and none of them are repeating roots of the characteristic polynomials. The associated eigenvectors for all the distinct eigenvalues, they are linearly independent. The proof is little convoluted, but let us see. Let us consider distinct eigenvalues of a matrix A, lambda 1, lambda 2 up to lambda j. The representative eigenvalues are x 1, x 2, x j. We need to show that they are linearly independent. So, we have the equation A x I is equal to lambda x I, and let us assume that so this x I is equal to, rather x I is equal to lambda I x I, lambda I is one particular eigenvalue, and let us assume that there is at least one non-zero C I for j plus, we consider j plus 1 eigenvectors, and there is at least one non-zero C I for which C 1 x 1 plus C 2 x 2 up to C j x j plus C j plus 1 x j plus 1 is equal to 0. So, there is one non-zero C I, that means C j plus 1, when we take x j plus 1, the j plus 1th eigenvector, that is linearly dependent with x j eigenvectors. This is an assumption we are making that, and on top of that we are also posing the condition that j plus 1th eigenvector is dependent on first j eigenvectors, where the first j eigenvectors are linearly independent. I assume that first few eigenvectors are linearly independent, and there is one eigenvector which is linearly dependent on that. How can we start that? We can take the first eigenvector, which is a single eigenvector, and assume another second eigenvector, the eigenvector 2, and assume that it is linearly dependent on that, and we will see that whether these things satisfy the condition that one eigenvector can be dependent on others, but few are linearly independent. As C k is non-zero, there is one C k which is non-zero, we can write C I plus j I C I j plus 1. So, C k is rather C j plus 1. as C j plus 1 is non-zero, we should write C j plus 1 is non-zero, C j plus 1 x j plus 1 is minus of this. And x j plus 1, because C j plus 1 is non-zero, so x j plus 1 is combination of the first j eigenvalues. Now, multiplying both sides by a, and we will use the fact that a x I is equal to lambda I x I, lambda x I, lambda I x I. Lambda is the ith eigenvalue. So, if I multiply left hand side by a, it will be a x j plus 1 is equal to b 1 a x 1, b 2 a x 2 up to b j a x j, and then a x j plus 1 is lambda j plus 1 x j plus 1. Similarly, for all other terms we get the relationship 2. Now, multiplying both sides of 1 by lambda 1, so we get lambda j plus 1 x j plus 1, and we get a equation lambda j plus 1 x, this is not k, this is lambda a plus 1 x, this is j plus 1, so wrongly written as k. Lambda j plus 1 x j plus 1 is equal to b lambda j plus 1 x 1 plus b 2 lambda j plus 1 x 2, etc. So, you subtract 2 from 3 and we get 0 is equal to b 1 lambda j plus 1 minus lambda 1 plus b 2 lambda j plus 1 lambda 2 plus b j lambda j plus 1 lambda t, and lambda j plus 1 minus lambda I is not equal to j plus 1 is not is equal to 0, because because they are distinct eigenvalues. So, in this equation these terms lambda j plus 1 minus lambda 1, lambda j plus 1 minus lambda 2 up to lambda j plus 1 minus lambda j, they are non-zero. And we also assume that b 1, b 2, b 3 at least all of them are non-zero, because c 1, c 2 to c j not all are 0. So, some of them are non-zero. So, we get an equation where we can see that this is equal to 0. As the eigenvectors are distinct and some of b's are non-zero, the set of vectors become linearly dependent. Our initial condition was that first few eigenvectors we assumed that they are linearly independent, and one eigenvector was linearly dependent on that. Now, we are seeing if one eigenvector is linearly dependent on the previous eigenvectors, the previous set of eigenvectors also become linearly dependent, and we can start with first two vectors and see that they should be linearly independent. And then we can go to the third vector and we will see that the third vector has to be linearly independent with the previous two vectors, otherwise first two vectors will be linearly dependent. So, the first clause is violated, that first j eigenvalues are independent if we assume j plus 1th eigenvector is dependent on the not eigenvalues, this should be eigenvectors. If we assume the first j eigenvectors are linearly independent, and then if we put then also assume that j plus 1th eigenvector is linearly dependent on first j eigenvectors, they are counterfeiting. So, this is violating the first clause. Therefore, any eigenvector cannot be dependent on few eigenvectors. Hence, we can start from first eigenvector and go to second and then carry on and say that all eigenvectors are linearly independent, and this is shown for eigenvectors which has distinct eigenvalues. For repeated eigenvalues, the proof will be different, and for real symmetric matrix we will see that all the eigenvectors will be linearly independent, but for distinct eigenvalues the eigenvectors are linearly independent. So, zero vector, another important observation is that zero vector is not an eigenvector of a non-singular matrix, because zero vector is always linearly dependent. So, only if Ax is equal to A is a singular matrix we can think of something like that, but otherwise zero vector is not an eigenvalue, because it is linearly eigenvector, it is linearly dependent on any vector set. n independent eigenvectors. Now, if we have a matrix with distinct eigenvalues, there will be n A is n into n matrix, square matrix. There are n distinct eigenvalues and there will be n eigenvectors which are linearly independent on each other. Therefore, n independent eigenvectors in Rn will form a basis of Rn. So, the eigenvectors will form a basis on Rn. Non-zero eigenvectors are obtained from non-singular matrix. So, they can form a basis. Eigenvectors form a basis of the column space for all distinct eigenvalues. So, there are n independent eigenvectors. These n independent eigenvectors are basis for column space also. And now, we can see that as we got a basis for column space which are eigenvectors, we can utilize the eigenvectors to get a diagonal form of the matrix A, or we will do some manipulation with the eigenvectors or some transformation of the matrix A eigenvectors, and we will get a diagonal form out of them. Eigenvectors can diagonalize a matrix. Let us consider n distinct eigenvalues of the matrix A, which is lambda 1, lambda 2 up to lambda n. The respective eigenvectors are x 1, x 2, x n. So, we will put the eigenvectors as the columns of a matrix S. So, it will be like S is equal to x 1 is x 2, and these are the eigenvector up to x n. These are the eigenvectors. This is a matrix S. Now, if we compute AS, AS is equal to A x 1, x 2, x n, and A multiplied with each eigenvector will be x, because we have the formula x is equal to lambda x, or for each eigenvalue lambda A x I is equal to lambda I x I. So, A x 1 is lambda 1 x 1, A x 2 is lambda 2 x 2, and A x n is lambda n x n. So, A x will be same column matrix X with the eigenvector, but each of the column multiplied with different eigenvalues. Now, the product matrix can be further shown as lambda 1 lambda x is equal to x 1 x 2. Again we can take eigenvalues and show that eigenvectors, its multiplication with eigenvectors into a matrix which is a diagonal matrix, and we only have the eigenvalues in the diagonal, and what we can write as S into lambda, where capital lambda is a diagonal matrix with eigenvalues in its diagonal. So, what we get? We got A s is equal to S into capital lambda, where lambda is a matrix with the diagonal eigenvalue, as a diagonal matrix with the diagonals have eigenvalues only. So, we get A s is equal to S lambda, and now S eigenvalues are independent. S is a matrix, S is a matrix with eigenvectors as columns. We are considering eigenvalues, eigenvectors of distinct eigenvalues. So, I assume that all the eigenvalues of A are distinct eigenvalues. Therefore, the eigenvectors are independent, as we have just seen earlier. So, S has independent columns. So, we will see that as the matrix S has is an n into n matrix with n independent column, S should be invertible. So, I can multiply the left hand side and right hand side by S inverse, and can write S inverse A s is equal to lambda. So, this is how we can diagonalize S. A, we have to multiply A pre-multiply by inverse of the matrix which has columns as the eigenvectors, and post multiply it by that matrix again, and we will get lambda, which is a matrix where the eigenvalues are only in the columns, or we can write A is equal to S lambda S inverse. Now, what is written is any matrix A will have all distinct eigenvalues or independent eigenvectors if it is invertible. Any invertible matrix can be expressed as a diagonal form. We can get a diagonal, we can diagonalize the matrix through matrix operation. Therefore, we can get a diagonal form of any matrix which is invertible, and the diagonal form, what will be in the diagonals? The eigenvalues will be in the diagonals. So, if a matrix can reach a diagonal form, that means the matrix is invertible. In that case, it will have distinct eigenvalue, independent eigenvectors or distinct eigenvalues, rather than vice versa. In case a matrix has independent eigenvectors or the matrix has distinct eigenvalues, we can get a diagonal form of the matrix, and we only get diagonal form of the matrix. Diagonal form means there is a diagonal and all other terms are 0. So, only the pivot terms are existing. Pivot terms, only all pivots exist for a matrix which is invertible. So, if the eigenvalues are distinct, the matrix must be an invertible matrix. And now, this is actually an important concept, but and we will see the utility later, that if a matrix A has eigenvalues matrix lambda, capital lambda, and eigenvectors matrix S, and now we take the matrix A to the power k, we multiply the matrix k times, and this will have eigenvalues as the matrix of as the eigenvalues of lambda to the power k. So, lambda 1 to the power k, lambda 2 to the power k up to lambda n to the power k will be the eigenvalue matrix, and same eigenvalues as A. So, we will see A is equal to S A S inverse. So, we put A to the power k S lambda S inverse, which is S lambda S inverse into S lambda S inverse k times, and all S lambda S inverse into S inverse into S, they cancels out, S inverse into S inverse into S inverse into S cancel out, but the first S and last S inverse exist and lambda exists. So, it will be S lambda to the power k S inverse. Now, this can be a quick exercise, that lambda is a diagonal matrix. So, what will be lambda to the power k, and which can be very easily checked, what will be the lambda to the power k. So, A to the power k can be very easily expressed as S lambda to the power k S inverse, and this also says, because lambda to the power k, and point to be noted is lambda to the power k is also a diagonal matrix. You can check it quickly, because A to the power k, because we can write A to the power k is equal to S lambda to the power k S inverse, which is a diagonal matrix, and it will have the eigenvalues of A to the power k. S and S is eigenvector matrix of A to the power k, because A is equal to S lambda S inverse. In this case, S is eigenvector matrix, and lambda is the as a diagonal matrix. Similarly, we get a diagonal form using S lambda to the power k S inverse. Therefore, S is also the eigenvector matrix of A to the power k. So, A to the power k and A will have same eigenvectors, and eigenvalues of A to the power k will be the the diagonals of the matrix lambda to the power k, which you can easily check what will be. This is very simple, but please check it, that what is this matrix, what are the diagonal components of this matrix. Now, we get couple of important definitions. What is a trace of a matrix? For a matrix A, the trace is the sum of the diagonal terms. trace of A is A11 plus A22 up to ANN, and this is equal to sum of the eigenvalues. Similarly, for a matrix A, the determinant of a matrix is the product of the eigenvalues. Determinant of A is lambda 1, lambda 2 up to lambda n, and this can be very easily shown by that term, that characteristic polynomial has roots lambda 1, lambda 2. So, determinant of A minus lambda I is equal to lambda minus lambda 1 into lambda minus lambda 2, lambda minus lambda n, and we will see that if we try to expand this lambda 1, lambda 2, lambda n and compare the powers in both sides, compare powers of lambda and lambda to the power 1 and lambda to the power 0 both sides, and then it will follow that comparing the power of lambda to the power 0 will follow the determinant loop, and comparing the power of lambda, compare the coefficients rather, compare the coefficients. Compare the coefficients of lambda to the power 0 will give you lambda 1 to lambda 1, lambda 2 up to lambda n. This multiplication is determinant of A. Similarly, comparing if you write the characteristic polynomial, and I will show you the characteristic polynomial in the next class, and comparing the powers of lambda, coefficient of lambda, which is lambda 1 plus lambda 2 up to lambda n, will give you the if you expand this and try to write it down, the trace of the matrix A1 A1 plus A22 up to ANN is equal to lambda 1 plus lambda 2 up to lambda n, or sum of eigenvalues. So, if we know the trace and the determinant, at least we can find out what is, or if we know that eigenvalues, we can find out what is the trace of the matrix and what is the determinant of the matrix. And this is also interesting because we will quickly see about similarity transformation, etc., the linear transformations in which eigenvalues do not of a matrix do not change. In that cases, the determinant and trace of the matrix will also not change. So, if we rotate the matrix, we rotate the coordinate frame, the matrix will change, but the sum of the of their diagonal elements will not change, as well as the volume encompassed by all the vectors of the matrix, that will also not change. So, determinant and trace are uniquely determined by the eigenvectors, eigenvalues, and therefore, with transformation they will do not change, and we can with coordinate rotation they do not change, transformation like coordinate rotation, and we can say that determinant, trace and trace are invariants of the matrix, which do not vary with the coordinate rotation. Okay. There is a few more important properties, that eigenvalues of A inverse is 1 by lambda, and these things can be very easily proved from just small exercise. Some of these problems may come in exams, and you can check it yourself. These are very straightforward, but this will be a good exercise if you check these things yourself. Eigenvalue of A inverse is 1 by lambda, and if there are two diagonalizable matrix A and B which share the same eigenvalue, this will happen if AB is equal to BA. If AB is equal to BA, then A and B will have same eigenvectors, not same eigenvalues, sorry, same eigenvectors. So, these are few important properties of eigenvalues and eigenvectors, and there are few more important properties for a class of matrices, and this class is called the real symmetric matrix. There are some important properties for another class of matrix which is called positive definite matrix. For the real valued matrix which are symmetrics, eigenvalues and eigenvectors will give some more important properties which we will discuss in the next session. Thank you.